Welcome to The Explainer. Today, we're pulling back the curtain on the hidden physics behind every great sports play. From that perfect free throw to a record-shattering javelin toss, we are going to uncover the invisible forces that make these moments happen. You know, a basketball shot is all about that delicate arc and precision, while a javelin throw feels like pure explosive power. On the surface, they look like they couldn't be more different, right? But what if I told you they are both ruled by the exact same set of physical laws? And that's what we're going to dig into. And that secret, it all comes down to the physics of projectile motion. Seriously, understanding this is a key to unlocking elite performance in pretty much any sport you can think of. So in this explainer, we're going to break it all down piece by piece so you can start seeing your favorite games in a whole new way. All right, so let's get into the nitty-gritty. What is projectile motion really? Well, it all boils down to two key forces that take over the split second an object leaves an athlete's hand or foot. Let's break them down. Okay, so we have to talk about vectors. Don't worry, it's simple. Just think of a vector as a little arrow that tells you two things: how fast something is going, that's its magnitude, and which way it's headed, that's its direction. It's the combo of those two things that gives you the full picture. Now, here's where it gets really interesting. These two vectors, the horizontal one and the vertical one, they act completely independently of each other. The horizontal vector just keeps things moving forward at a steady pace. But the vertical one, it's in a constant battle with gravity. This separation, this is the absolute core idea of projectile motion. So picture this: the horizontal vector is just cruising along, steady as a rock. Meanwhile, the vertical vector is on a total roller coaster. It shoots up, slows down, hangs there for a split second at the very top when its value hits zero, and then gravity takes over and yanks it back down, faster and faster. Okay, so that's the perfect textbook model. But, the real world is a bit messier, isn't it? Things get a little more complicated out there, and not every object flies in that perfect, clean arc we just talked about. I mean, have you ever really watched a badminton shuttlecock? It seems to almost defy gravity. It blasts off the racket with so much speed, and then it just seems to float before dropping like a rock. This is a perfect example of how the real world messes with our perfect model, and it's because of one huge factor. And this right here shows you exactly what's going on. A heavy, dense object like a shot put just powers through the air. It follows a beautiful, almost perfect symmetrical curve. But then you look at the shuttlecock. Because it's so light and has that wide cone shape, its flight path is all distorted and lopsided. So what's the difference maker? It's one thing: air resistance. You can also call it drag. It's literally the air pushing back against the object, slowing its forward motion and making its drop-off way steeper on the way down. It's the whole reason a shuttlecock seems to hit a wall midair. Okay, so if you're an athlete, you're probably thinking, I can't change gravity and I can't just get rid of air resistance, so what can I control? Well, that's a great question. There are three key things you can control to get the most distance possible. Let's open up the athlete's toolkit. It really boils down to these three things: the height you release it from, the speed you release it with, and the angle you launch it at. Think of them as the three levers an athlete can pull to perfectly tweak how far something flies. Now, all three of these are important, don't get me wrong, but one of them is the undisputed champion, the one that makes the biggest difference by far, and that's the speed of release. In the world of projectiles, speed is king. Let me tell you why. The reason is that the relationship between speed and distance isn't linear, it's exponential. A tiny bit more speed creates a huge increase in distance. That's why throwers will train for years just to add a single mile per hour to their release. They know it translates to feet, not inches, in their final result. All right, that brings us to our final piece of the puzzle: the angle of release. And there's a huge myth about this that we need to bust right now. I bet you've heard this one before, probably in a physics class. To get the most distance, you have to launch something at exactly 45 degrees. But is that actually true in sports? If you watch elite athletes, you'll see they almost never use that angle. And there's a very good reason for it. The short answer is no. See, that whole 45-degree rule only works in a perfect little physics problem where you launch something and it lands at the exact same height. But how often does that happen in a real sport? Almost never. Just take a look at this. In sports like the shot put or the long jump, the athlete is releasing from up high, maybe 6 or 7 feet, but the object is landing down on the ground.
Because you have that built-in height advantage, the best angle is actually less than 45 degrees. You can trade a little height for more forward distance. That 45-degree rule really only holds up when the start and end points are on the same level, like a soccer kick from the ground. So from now on, when you're watching sports, you'll see it. You'll see the physics behind that perfect three-pointer or that incredible javelin throw. It's not just raw power. It's a beautiful, complex dance between human skill and the fundamental laws of the universe. This explainer was based on the biomechanics section of the Cambridge AS-level Sport and Physical Education syllabus. It was brought to you by Revise Direct. Thanks for watching.